Perfect. Perfect. Go ahead, please.
Martin was very fast. Yeah, thanks first of all for inviting us or me on this talk. Good morning to the US, good afternoon to Europe, and I guess good evening at least to the people in India. I'll try to share. I'll have a go at this thing with Rise going in big, but let's see how far I can get because there were some comments in the chat before. Please feel free to complain.
So I see some square at right-hand side. Do you also see that?
Yes, I think it's the thing from Zoom. I'm sorry for that.
Okay, there's a big block
somewhere
right.
outside the view.
There's
is it gone?
Right there where your mouse just was as well.
Is it still there or is it gone?
No, there's a different one. You got rid of the first one, and now there's a very large one. The edge is
top here
and source in, and then we can't read anything else.
Oh my God. I thought I had solved this before.
There
okay.
Now it's gone. Now it's gone.
So now it's gone, and if I go for F11, it's there.
No, so it's fine. It's fine.
It's good now. Okay, then let's just go ahead like this. So this talk is a bit about integrating GPU libraries for fun and profit. It's talking about two HPC simulation tools. I'm coming also from the beam dynamics community, and I've done a lot of work together with Martin, who just talked beforehand. This is just the abstract of our talk again for comfort. Let's just go for the physics. So I'll talk a bit more about simulation and how to put together different simulation tools on the GPU level without getting a lot of performance problems. So what we typically do in beam dynamics, in collective beam dynamics, in fact, is to follow the 3D particle motion. So you have something that is describing the particles with 6 phase space coordinates in the horizontal, the vertical, and the longitudinal. And then we would call a beam a state of n such particles, or in numerical code macroparticles, so that we would have for each of these an array of n length, so in total 6n values of phase space coordinates. Just to give you an idea. Simulations typically use up something until 1 million macroparticles. We want to track around the accelerator. So for example, in the LHC, it's something on the order of 1,000 to 10,000 elements, depending on how you're setting up your map. And such simulations, they can typically last, depending on what effect you want to look at, up until 1 million turns. So you can see it's adding up a lot of arithmetics. And while we're going around the accelerator, we want to include some particle-to-particle interaction. So there will be some binning, some FFT or convolution algorithms. For space charge, typically we're using particle in cell or some person solving things. So it becomes very heavyweight. What I wanted to say here is mainly that in the simulation tools, we really require something that is stable on the long-term evolution. So we want to deal with double precision numbers. It's heavy number crunching typically, so we rely on high performance computing techniques, in particular for collective effects. And what very many times happens is that we have to have an iterative development. So we need to change the way our simulation works many times. There's a frequent update of the accelerator models, which makes it nice to use it from the Python side and deal with things on the Python side. But then on the other hand, we need this high performance computing part. So you see where this is going. Here I'll just talk about the two different areas of beam dynamics, let's say. Single particle is something that is embarrassingly parallel. So there we just want to have a look at n different particles and how they go through the accelerator. We call this tracking. I will denote it in blue throughout the talk. And this is really just following the particle motion due to the magnets and the radio frequency cavities in the machine. And then we have typically some multi-particle effects. So I'll call this a collective effect, kick. And this is where we model the direct or indirect particle-to-particle interaction. So you can typically imagine going around the accelerator, something like this in our model. We're starting from somewhere, and then we go, track through the elements, have some interaction, track through the next elements, have some interaction, and so on. Yeah? So I'll talk first about the PyHEADTAIL library very briefly. It's a Python-based code for simulating collective beam dynamics. Here's the GitHub repo. It relies on very simplified tracking, so it has some matrices built inside. It's a very effective model, but this code is very strong on detailed models for collective effect kicks. So this is an example where we have a particle going through some kind of structure. like a nice detector, for example, with an opening, and it will leave behind some electromagnetic waves and wake field, which can interact with trailing particles. This is a typical thing that we simulate very often, for example, for LHC. And there's another library that we've just heard of, the SixTrack library. This one is C-templated code. It has a Python API, as you just heard, and it's mainly for simulating single particle beam dynamics. So this one is really strong at advanced nonlinear tracking. It really takes all the different elements in your accelerator layout and maps properly through them. And it has also some simplified models for collective effect kicks, but the strong part really is the tracking. Now we come to the HPC part. I had actually presented PyHEADTAIL on the GPU, or at least the concepts behind, on the last PyHEP, just half a year ago, or a bit more. The idea here is that we're utilizing duck typing, just briefly, to separate the physics from the backend implementation. So you could throw in NumPy arrays or GPU arrays from something like PyCUDA or CuPy, yeah. Then we have designed a sandwich layer via context management and function redirection, which I talked about in detail. So what we're really doing is just having a separate math library in the end. Huh? So if I want to call the sign on the CPU, I will just redirect to a NumPy sign. And if I want to do it on the GPU, I call the corresponding GPU library. And then we can just use PyCUDA in the end and exploit the GPU, similarly with CuPy. Okay, so what typically the inner loop of our simulation looks like, or let's say that the central part of the simulation, you're setting up everything in Python. You have your beam somewhere, and you first of all transport the beam onto the GPU. Then you will go for a number of revolutions around the machine, and going through each element in this list of elements here. And each of these elements has a so-called track method here that will just transport the beam from before to after. So this is just the inner loop. Huh? Typically, these element track calls, they're very heavy, so you don't lose a lot for running this on the Python level, this loop. But it gives you all the access to the inner part. Let's say you can restructure your simulation, your accelerator model, and so on. So this looks always the same. The only change that I do from CPU to GPU computing is to change this context here that we have implemented in PyHEADTAIL in this way, just to deal with all the transfer of memory and so on. So outside of this, we're sitting in NumPy. Inside of this, for example, we're sitting in PyCUDA on the GPU memory. This is very transparent to users, or also to the high-level developers that just want to write some kind of track function. And I'm anticipating some discussion afterwards on number as well. This is typically very difficult to implement a number because this PyHEADTAIL beam object here, it has a rich structure behind. So depending on what kind of element you're using, it can be a different argument signature that you want in the end here. So to us, it was really difficult to find a way with number. But anyway, the way we've set it up with GPU arrays already works very fine, because typically some low-level calls that take a lot of time in your simulation. For example, when you're calling the QFFT library, then most of your time is anyway spent inside this library. Good, so far for PyHEADTAIL. I'll quickly talk about SixTrack on the GPU, which we've heard already before, and in more detail actually also last year where Martin was talking. It also has this Python API for dynamic interaction. But by itself, the code, as we heard, is a C-templating approach. This is here the idea to separate the physics from the backend implementation, so it becomes more maintainable in that sense. So in the end, you're just implementing this template once in Usual C, for example, for the single core CPU, or you could do it in OpenCL for multi-core CPU or GPU stuff, both for AMD and NVIDIA types, or you could even go as crazy and put this on other stuff, but usually we just stay here. And the implementation finally in CUDA for NVIDIA GPUs. Okay, so typically what this looks like from the Python level is we are defining our track job from SixTrack, and then we provide it with some description of the accelerator. We provide it with a description of the particle beam, and then we tell it on which device it should run. So for the user perspective, you're just changing the device here, but you're not really having access to the inner loop. You see that? So afterwards, we define this track job, and we just tell it, hey, track for 10 million turns around the machine, and come back and tell me what happened. This is the way how you usually interact with SixTrack. So the quest, the idea behind all of this. clearly, I want to marry the two, right? So SixTrack lib by itself is a code that is strong in the advanced nonlinear tracking part, while PyHEADTAIL is strong in collective effect kicks. So why can't I just unify the two into one thing, and they are strong in both? So that would look like something, if I take again this picture that we had before, where we're starting somewhere in the ring, we transport the beam with SixTrack lib, we kick with PyHEADTAIL, we transport again with SixTrack lib, we kick with PyHEADTAIL, and so on. So that would be like some kind of alternating calls for both libraries. And you can immediately see that there's quite a lot of questions on this. So just to quickly explain the situation, PyHEADTAIL on the GPU by itself, it lives inside the PyCUDA environment, and everything is managed from the user scripts on the Python level, as you saw before. While SixTrack lib on the GPU, it manages its own CUDA kernel invocation by itself. So already talking about the way that the beam data is stored, we have PyHEADTAIL with the PyCUDA GPU arrays, and SixTrack lib by itself has some custom memory buffers. So there's a lot of memory handling internally. So you can already see there's some critical aspects. How can we hand over the data between the two codes? How can we avoid a very costly GPU to CPU to GPU memory transfer? So you want to stay on the GPU to really profit from this and not go back to the CPU just to hand over. And this brings the question, how, if I call a context or start a context within PyCUDA for PyHEADTAIL, how would this interact with SixTrack lib, which has initialized its own context? So how is memory visible to each other? And can we call kernels once from PyHEADTAIL, once from SixTrack lib? And can we control all of this from the Python level? That's what this talk is about. And I hope to show you a few funny things. And if you're not really into this low-level stuff, at least I hope you take away a little bit of crazy beam dynamics. But it's a start. So let's enter into an example simulation. For the moment, just with PyHEADTAIL, because most of you are familiar with the LHC, I'll just take this example here. So we'll just take a coherent instability in the LHC. This is typically what happens when you guys don't see stable beams on the monitor, but we guys get to play around in the control room, hopefully not too strong, so that the whole machine breaks, but okay. So I'll just start. I've hidden all the matplotlib, numpy stuff, Python path setting inside those imports here. It's in the same repository. And to import a PyHEADTAIL, before just call a context for PyCUDA and then import PyHEADTAIL. You will need to use the develop branch of PyHEADTAIL to make this notebook work as I have it run today. Just for reference, here's the commit that I'm running on. So if I track around the LHC ring, I will need to have some transverse tracking for XX prime and YY prime. So I will take some transverse tracking. This is typically a matrix. I have hidden away all the LHC parameters inside this file here, which is also in the repository, and I can just provide it here to this transverse map. Good. And then we want to have also some longitudinal tracking. For this, we have some RF systems. Also, again, here, I've stored away all the numerical parameters, so we don't need to bother with this. And finally, we want to have some collective effects. So we can go around the machine inside PyHEADTAIL. Now we want to add a wake field. So here I'll just add a broadband resonator. It's dealing with the accelerator like a big circuit, let's say. So we will define a circular resonator here, and I need a slicer. This is the binning that I was talking about. So you guys usually do histogramming for particle physics. We do histogramming in order to make the beam discrete and handle it numerically much faster. But in the end, we're all talking about histograms. Okay, so here I have my resonator wake. That's the picture here, as I showed before. So let's just assemble the transport map around the LHC ring as it happens in PyHEADTAIL. So I'll have this list, which has some transverse map inside, longitudinal map, and this wake field, just together. Now I still need the particle description. So I'll start running this part here. I've done some stuff to actually make things a bit faster for the demo here. So this is strictly speaking not needed. I will launch a bunch with 10,000 microparticles and an intensity that those of you who know LHC a bit, this is quite a bit higher. So we will run into an unstable situation just for the fun of it. So let's initiate this beam here. It's a Gaussian 6D beam. And just to have a look quickly how it looks like. Perfect. In the horizontal, we have something Gaussian. In the vertical, we have something Gaussian, and along the longitudinal plane as well. Good. So we'll just give it an initial offset in the vertical just to see what's going on. 10% of the beam size, that's not too much. And we just saw a blueprint how the bunch looks like for later. So let's go ahead. So this is all running with an NVIDIA GPU in the back. So maybe you want to quickly show this. NVIDIA SME, you can see this. This notebook is running on the GPU number 1. This is a GeForce RTX 2080 Ti, just for reference. So we will want to run on that one. So I'm importing this context manager from PyHEADTAIL. I tell it I want 500 turns. I transfer my PyHEADTAIL beam into the GPU, and at the exit of this, it will automatically go back to the CPU. I just provide some array here so that I can store the vertical bunch centroid just to look at what our beam is doing. And afterwards, I have exactly the same loop that I was talking about before. So first we go through all the turns, and for a turn, we go through all the elements in this ring. Remember, there was a transverse, a longitudinal map, and some wake field in there. And each of these just tracks the beam. After this one round, we store where the beam is sitting at the moment on average, and we will have a look at how this goes. So this is a rather fast simulation. And we're done already. Now I get back this array to the CPU. And let's have a look what it has done to our bunch. Oh, so there's a clear instability developing. You see that it exponentially grows. This is the position of the bunch in the vertical. And quite rapidly here over the 500 turns, we're already at 1 centimeter. So you guys wouldn't like that too much if it runs into the detector. But okay, it's a start. So this kind of simulation is typically what we do inside PyHEADTAIL. Here, we're just using something very, very simple for the tracking. Wait, I'm advancing a bit too fast here. I have another picture just to see how the instability develops along the bunch. So this is the longitudinal direction. And here's what you would see in a very fast wideband pickup, where you could see how the bunch starts to oscillate really, really strongly. So that's this transverse mode coupling instability here, for those who are interested in the beam dynamics. Okay, so let me get back to what I just wanted to say. The LHC accelerator layout here was simulated with a simple matrix. So just to go through this entire story without any wake field, just to show you what really was happening. I just got something oscillating normally. This is really a very simple model for the tracking. So SixTrack lib actually can simulate the real lattice, shall we not? So I have an example simulation with SixTrack lib tracking around the LHC. I will import SixTrack lib here. I've already gone through the hassle of the CMake stuff, so thanks a lot to Martin for making this so easy. For those of you who want to install this notebook, it's really nice and well documented to go through. So we'll load the LHC lattice from something that even comes along with SixTrack lib. There's a test data LHC in there. And we'll just add a monitor to look what our beam is doing. We'll use 1,000 macroparticles and go for 200 turns. And to populate this, I will just exploit the PyHEADTAIL generation here. I'll just make a bunch and inject this into an empty SixTrack lib particles instance here, okay? That makes life a bit easier here. This is all on the CPU still because we have done nothing crazy yet. This is just the buffer on the CPU with elements here that are actually NumPy arrays. Oh, I think I'm generating on the other slide. So just to look at this, this is really just a NumPy array. Huh? So the GPU stuff comes afterwards now. And here I go, having injected stupid stuff. So actually, SixTrack lib particles hold a few more longitudinal coordinates just for convenience in comparison to PyHEADTAIL. I will have to initialize them as well. This is a technical detail. Now, here we go to the inner part of SixTrack lib. I will define my track job and I will run it on OpenCL here. So the same NVIDIA card. And I will quickly run this. And really to make sure that we're seeing something nice here, should quickly go to the machine and be fast enough. You can see that it's running at 100% here. So this is really the OpenCL now. Okay, and it's back already, so it's fast enough. Oh, I'm very sorry for this. Where was I here? Wrong button. Good. Then I'm coming almost to the end already. The fun part where to put the two together. But before that, let's just have a quick look at the output. So we've just tracked, took a short while, a bit longer than the matrix model, but okay. And we see there's some tracking going on, and clearly this is a bit more than just a linear matrix model. There's already some cool stuff happening just from the tracking side. So SixTrack offers more complex kinetics than just using a matrix like in PyHEADTAIL. So let's try to unify those two, shall we? We want to integrate the SixTrack tracking with the Wakefield kick from PyHEADTAIL. So the starters menu, we will just do it for one turn using SixTrack to track around the complete ring so that we don't have to enter here, and then add a PyHEADTAIL Wakefield kick so that we can actually take turns between those two. It makes it a bit easier for the demo here. The flow control is supposed to stay on the Python level. Which library takes over when will be defined on the Python level. So the idea that I have here is to actually track through these number of turns here, and first have SixTrack where I have some ominous function here that transports my PyHEADTAIL stuff to SixTrack. Then I will run SixTrack to track until the next turn. I transport back to PyHEADTAIL, and then I run the PyHEADTAIL Wakefield track. Ideally, all of these functions, they don't do anything but stay on the GPU device and just tell the respective code where to look. So how to define those two functions? Let's start with the direction from SixTrack to PyHEADTAIL. And this is where the fun starts. I hope some of you take away a bit. So let's just take a GPU pointer that is constructed by SixTrack and construct a PyCUDA GPU array around it. We're entering a bit the black magic here, so I'm just restarting my PyCUDA. And we have this function here that provides a PyCUDA array by just taking a GPU pointer, any number, and the length of it, and it constructs this array. So you can already see this is going in a funny direction. So the approach will be that we use SixTrack CUDA track job now to use the dedicated CUDA implementation and stay in CUDA in both codes, so not OpenCL anymore. And we will prepare some GPU memory as an example in SixTrack and then we will build a PyCUDA array around this memory for PyHEADTAIL. So let's do that. I build the same beam here, empty. Again, I just have a look at this array here. It's just a numpy array.x. And I will populate this numpy array with some a range here, okay? So how does it look like? The first 10 elements, they're just increasing here. Cool. So this is on the numpy array in SixTrack now, in the buffer. Next thing is we actually want to go to the GPU. So we have to define the track job again, and this track job will allocate the GPU memory and fills it, among others, also with this SixTrack beam.x array. So let's ask the CUDA track job for the particle addresses here, just to get the address of this particular part of memory that it stores. And we get back some kind of a pointer address. Now, here we go. We provide this to PyCUDA, you remember. And this has a length of number of macro particles inside. So here comes the black magic stuff. I provide this to the PyCUDA level now, although it has been created inside SixTrack. And indeed, I can see an array that is filled with exactly the same numbers as we had them before. I remind you, in the meantime, SixTrack has done this transfer to the GPU for us. So the type of this array is actually now a PyCUDA GPU array here. Cool. So we can construct it this way. It's filled and allocated in SixTrack. SixTrack will be able to track something like this. And we have the direction SixTrack to PyHEADTAIL covered by just using this array in PyHEADTAIL afterwards. Let's go for the reverse direction, PyHEADTAIL, which is all the Python stuff, to SixTrack. The thing is that in PyHEADTAIL, during a track, the GPU arrays that are constructed, they are not necessarily in the same memory location anymore. I will show you this. Let's simulate some tracking update by PyHEADTAIL. So we'll take this X GPU array and square it and do +1, and all of this will be happening on the GPU, and we will put it here. You can see the array has changed. And now here I'm really asserting that the two GPU data pointers are not the same anymore. If you want to go into the detail here, you can see afterwards these numbers are different. So they are not residing inside the buffer of SixTrack anymore, and I will have to copy the data back into the fixed buffer in SixTrack. For this, I can just use the driver from PyCUDA and do some device-to-device memory copy. Good. Now let's check that this has really been written back to the SixTrack buffer. So again, we take this location inside the SixTrack buffer and provide a GPU array. And indeed, now we see this updated array. So just to see whether SixTrack can also transport them back to the CPU, we collect the particles. That's the way how to do that in SixTrack. And I have a look, and indeed, I see these different numbers here. So the buffer has been filled with the updated values of X, everything works, and we can collect the updated data back to the CPU memory after it has been done on the, after it has been tracked on the GPU device. And I'm coming to the final part here. So let's plug all of these things together. At this moment, in fact, just to make sure that we are not messing up all these different devices, I will just restart the kernel, not the devices, I'm sorry, the contexts that I've been calling on and off before. So we'll restart freshly. I will import all these things that I had before, so nothing new here. I define the two containers. So that's the PyHEADTAIL beam that we want to do stuff with, and that's the SixTrack beam. So both of these are just the containers for these arrays of X and X prime and so on. I define my accelerator. Again, this time I will take the one from SixTrack, so the nice LHC layout with all these 1,000, 10,000 elements. In fact, I could look inside just to see how long it is. So there's 18,000 elements in here. And we can just look, for example, at the first two, a few. So there's drifts, multipoles, and stuff going on, you can see. So there's quite a lot of stuff beyond the matrix model. And here we define the same story as we had in PyHEADTAIL before, our wake field. And now comes the preparation for the GPU device data transfers that we want to do afterwards in the tracking. So we will first take all the buffer pointers from SixTrack and store them inside this array here. And also for the other way around, we will need this mem copy as we had it before. Here we'll do it in synchronous just to be a bit faster. So the one function, just implementing what I did before for just one array for all of them. It looks a bit scary, but don't worry about this. It's just all the little details that we've done before. And finally, the function to go from SixTrack back to PyHEADTAIL. So here I just need to make sure as a kind of barrier that SixTrack has finished its kernel. So I will just collect the particle addresses once more instead of calling a barrier. That's the same effect. And I will just take the buffer arrays here and store them back to PyHEADTAIL. Simple as that. And theoretically, we should be ready for tracking now. So instead of going for 500 turns now, I'm only tracking 11 turns. As you could see before, it took already quite a while to simulate the LHC in SixTrack. So here, what are we doing? We're going to the GPU with the PyHEADTAIL beam. Again, we just make an empty array where we will store the motion of the beam. And as before, we have the loop for the number of turns that we want to go around. On the SixTrack side, now I take this PyHEADTAIL stuff that I've just transferred to the GPU device. I make SixTrack known to these. I run the CUDA track job until the current turn. And finally, I will transport this back to PyHEADTAIL. And there I call the wake field track. And after I've done this for one turn, so we've gone around the machine, we've kicked, I will store what happened to the beam. This time, if you've watched closely before, I've actually increased the intensity by a factor of 10. So we expect a very strong instability here. And indeed, you can see this is something that goes off exponentially very fast. So over 10 turns, we're already going to 0.3 millimeters. And if I just had tracked for 5 more turns, you would see this already in the 10 to the 7 or something. So this was tracking with a realistic lattice in LHC. And indeed, we can have some kind of displacement of the bunch along the bunch here in the same way as before. So cool, we can have both libraries work together. Let me conclude this. You've seen in action a duck typing approach to GPU computing with PyCUDA. This is the PyHEADTAIL library. You've also seen in action the templated library SixTrack before that supports both OpenCL and CUDA that I've run live here for GPU computing. And finally, the fun part of this was the reunion of both. So we made sure that we're remaining on the GPU device memory so that we avoid going to the CPU instead in between. And we could indeed alternately call those kernels from both libraries just to update the bunch state of our beam. And all of this was done with a flow control from the Python level, so I could just decide to make this arbitrarily complex here. The advantages of this approach, just to have a few thoughts of mine here, you have a very rapid adjustment of physics, of the physics model that you can do here. So this kind of approach, it really saves doing all of this on the Python level, really avoids a lot of person hours when you're developing and you're just quickly running this new scenario. Oh, we had an instability in LHC yesterday in reality. Can somebody reproduce this? And you just need to make sure that all the things that were run on the LHC setup yesterday were implemented properly in your model. This Python stuff rapidly speeds this development process up. With this approach, also both libraries, SixTrack and PyHEADTAIL, they remain standalone simulation tools. So we haven't modified them a lot, and this avoids a tight integration. And nonetheless, we could really, really profit from this GPU speed up here, as long as the simulated physics is heavy, somewhat heavy. So what I said before is that these track functions that we were looking at before, they should really be some heavy stuff like calling QFFT or doing some particle and cell stuff so that the Python overhead really becomes marginal. If you're just doing a computation of 1 + 2, then this will be a very bad approach. Good. And finally, a funny thing that we found out when trying this the first time, as I had several GPUs on this machine where we tried this, CUDA offers unified memory. So somehow we ended up tracking between 2 GPU devices, which was a sort of surprise, but this is a straightforward way how to extend to several GPU devices without worrying too much, just with the recent CUDA versions, of course, but this is really nice. There are some disadvantages to this, clearly. In the interface that I've presented here, we needed some low-level pointer arithmetic, but in the end, if you're really defining something like this, you just define it once and you store it away in a nice class that you just call from the user level. The other thing that one needs to be careful with is memory deallocation. So we now really need to take care which context does the allocated memory belong to and who's modifying it and who's maybe forgetting about it. So this is something that you need to make sure it works properly if you're really building a more complicated, sophisticated tool on top of this. Okay, so to finalize this outlook here, in this notebook, clearly I've just given a mere example. So this is not the usual use case that we try to simulate with this, but it was fast enough for a demonstration. This starters menu that I've presented here that consists of 1 turn equaling to a complete ring in SixTrack and then 1 single PyHEADTAIL interaction. This is of course a bit particular here, but it can be generalized to have arbitrarily many stops during the ring tracking. And for this, in fact, Martin has kindly provided some new API in SixTrack, which doesn't only allow you to track until a turn, but also track along the line from some element to another element. So clearly now you have all the interface in SixTrack also to just inject stuff. And in fact, here I've added a notebook link that I'm running with realistic simulations in. Many, many thanks. We hope you enjoyed. And just to quickly show, this is this notebook that I was just linking to. Here you can really have detuning from space charge. You can have things that are really heavy weighted, and they run half an hour instead of 2 days on the CPU. So this is really profiting from the setup that we have here. Good. Thanks a lot.
Thanks very much, Adrian. That's really very interesting. Of course, it's very also different from what we do, well, most participants probably do.
Yes, I realize that.
No, but it's quite interesting, and there's lots of things that are relevant to us anyway, also from experience. I also particularly appreciate the fact that you guys managed to bring up the strengths of the 2 packages, but not tightly connecting them. So actually building something from like an ecosystem, like a tool set, which is something we always try to do that as well in various projects. I think it's very nice.
So I'd say the bottom line of this presentation was more or less our surprise how easy this was, because if you're touching this in the beginning, you're thinking, oh my God, I'm going to be thrown against the wall in so many ways, but that seem to work so far. So I'm waiting